So in this section, we have found all real solutions. So that's the rational and the irrational. The rational ones we had on our list of candidates. The irrational were the ones with the radicals that we use the quadratic formula for. Now the process is the same, but we're also finding complex solutions or imaginary solutions. So they're going to have I in them. And we have a theorem called the Conjugate zeros theorem. And it says, in a polynomial with real coefficients, if a complex number is a zero, then its conjugate must also be a zero. And this really just kind of helps us out because, like, if we find that 3 plus I is a zero, then we know automatically that 3 minus I must also be a zero. So they come in pairs. And then lastly, the fundamental theorem of algebra. It says every polynomial with complex coefficients has at least one complex zero. So, I mean, this is true. A complex number doesn't have to have an I. It could be like 4 plus 0I, which would then just mean that it's 4. Whoops. And then that could be considered a complex number. So a complex number doesn't have to have I, but all this is saying is that it'll have at least one complex zero. Okay, so again, we don't really use too much the fundamental theorem of algebra, and the conjugate zeros theorem is just something to be aware of. But our process is basically the same. So even if we didn't even talk about this, our process is the same. So my p-values are going to be 1, 2, 4, and 8, because those divide into the last term. My q values are going to be just 1. And again, I really like when my q values are 1 because for p over q, it's just going to be all of these numbers. So plus minus 1, 2, 4, 8, because whenever you have 1 as the denominator, it's just the whole numbers. Okay, so I need to make a guess, and I'm going to make a good guess by using the calculator. So if you graph this function on the calculator, and I just graphed it on the standard window, then it looks like this. And this is kind of interesting because with a degree 3 polynomial, there should be 3 solutions, which also means that this should cross the axis 3 times, or it may bounce off the axis, and remember, any time it bounces off the axis, that counts for 2. But it only is really going through it once. If you zoom out, you won't see any other intercepts either. So this is kind of interesting. Let's keep going. It does cross here at -2, and -2 is on my list of potential candidates. So -2 is going to be my good guess, and I'm going to use synthetic division. So bring down the 1, this will be -2, 0, 0, 4, -8, and 0. So I can officially declare -2 as one of my zeros. And we now have a quadratic. This is x squared plus 0x plus 4. So again, once you get it down to a quadratic polynomial, then you should use the quadratic formula. So that's going to be x is equal to -0 plus or minus square root of 0 squared minus 4 times 1 times 4 all 2 times 1. And if I simplify that, this is just 0, so I don't even really care about that. This will be plus or minus square root of negative 16 over 2. Square root of negative 16 is going to be 4i. So square root of regular 16 is just 4. So square root of negative 16, because we are considering imaginary numbers, it's going to be 4i. And we still have that plus minus there, and we still have that 2 on the denominator. So then if I reduce the 4 and the 2, I get plus or minus 2i. So I have positive 2i, and I have negative 2i. And again, that's really what the conjugate zeros theorem was talking about, is that these come in pairs. So because I have 2i, I kind of knew already that I would have negative 2i. But it also kind of naturally just comes about by the quadratic formula, because in the quadratic formula you have this plus minus here, which kind of guarantees that it's going to be a conjugate. So these are our 3 solutions. It's a degree 3 polynomial, and we have 3 solutions. And the reason why we don't have 3 intercepts is because these are imaginary. They're not going to cross the axis. So this one crosses the axis, but these imaginary solutions, they count as solutions, but they're not going to be x-intercepts.